So good morning everyone, welcome to Kaexchem. And a lot of you told me that this background here, it did not look good. So I changed my app and it should improve your experience of viewing, and I also turned off my fan. So let's begin with thermodynamics part 1. We will be covering the basic definitions in this part. So let's begin. And once again, this video, it is not for first timers. You must have a basic understanding of thermodynamics because this is meant to be a revision video, not a theory coverage video. Although this video is designed so you can fix your own theory gaps, because this is one of the most conceptual chapters in chemistry, and so let's begin. First, let's talk about system and boundary. Basically, a system is the part in observation. Like in thermodynamics, we will be looking at a certain system and we will be deducing terms. Like basically, we will see internal energy, work, heat, all of that. We will define all of those with respect to the system. So, for example, a mixture in a flask, whatever that we have in observation is called a system, and everything outside the system is called surroundings. Obviously, if I add system and the surroundings, I get the universe, and the interface between system and surrounding is called a boundary. So the types of boundaries are, first of all, diathermal boundary. It allows heat exchange between system and surrounding. Adiabatic boundary, which is insulating, and it allows zero heat exchange. And these are the types of systems. Open systems, they exchange mass and energy. Closed systems, they exchange energy but don't exchange mass. And isolated systems, which exchange neither. Now let's talk about extensive and intensive properties. Basically, extensive properties are those properties which depend on mass, volume, or amount. Basically, any property that scales with more number of particles, more mass of particles, or more volume of particles added to our system. Any property which scales according to that addition, or anything that is directly related to the amount of the substance in question, that is called an extensive property. But if it doesn't depend, then it is called intensive. For example, mass and volume themselves are extensive properties, since if you add more particles of the substance to an already existing specimen of the substance, its mass increases. But density is intensive because even if you add those particles, the density remains constant. So extensive properties are additive in scalar manner. You see how mass can be added like plus 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 2 plus 3 plus 4. That is scalar addition. And ratio of any two extensive properties is intensive. For example, mass extensive, volume extensive, but mass upon volume is intensive, which is density. And specific means per gram. Like if in any property you see specific, that means it is that property expressed per gram of the substance, and molar means per mole. Both of these terms in front of a property imply an intensive property like specific heat or molar heat. All energies like kinetic, potential are extensive. You see kinetic is half mv square, so it depends on amount. And potential, say in gravitation, g m by r, so it depends on mass again. So yeah, all temperature points like boiling point and melting point or triple point or whatever, they are all intensive in nature. And these are some properties which are extensive or intensive. Take a look at them. So continue, and let's now look at what is state and state function. State is, it's nothing but the current condition of the system, and we will restrict our discussion to ideal gases for now. To perfectly describe a state of ideal gas, we need three variables. You know the equation PV is equal to nRT. Since R is a constant, we need three variables out of PV and T. So we can describe the state perfectly, and the fourth can be discovered using the equation itself. And what is a state function, you may ask? State functions are functions that depend only on the state of the system and not the path that was taken to achieve that state. Path function depends on path, not state. So to say this, let's look at an example. Basically, these are two people, Elon Musk and Palak Ande. So basically in 1990, Elon Musk had 100 rupees and Palak Ande had 0 rupees. But in 2026, Elon Musk still has 100 rupees and Palak Ande also has 100 rupees. The story goes, Elon Musk has the same amount of money as Palak Ande, but Palak Ande had to work harder to get the same amount of money, while Elon Musk inherited it from its father. So this shows that money is a state function, but hard work is a path function. Palak Ande had to do hard work to get to that money. And we can see both of them are at the same state, but in 2026, but none of them, what am I saying? Both of them don't have the same amount of hard work. Elon Musk did no hard work and Palak Ande did all the hard work. Okay. So, and lastly, if we come back to our domain of thermodynamics, pressure, volume, temperature, internal energy, entropy, enthalpy, Gibbs free energy, these are all state functions, and their changes like delta P, delta V, and so on, they all are also state functions. And examples of path functions are work and heat. Here also hard work was a path function. So now we have talked about these. We have said that these are state functions, but now we need to learn about them in detail. So first, let's look at internal energy. What is internal energy? This is the energy associated with an object. Like it is the energy which is part of the object itself and it founds derivation in the existence of the object itself. Okay. It is not given to the object. It is the energy which is the virtue. Basically, it exists with the object. How do we define internal energy? It is the sum of kinetic energy of microscopic level random motion. Not ordered, only random motion is considered. And for a real gas, the internal energy depends on pressure, volume, and temperature. But if we talk about ideal gas, and as I said you, we will restrict our discussion to ideal gases. So for an ideal gas, it depends only on temperature, and we will see later. Its absolute value can't be found. We deal in change. So this is like the potential in physics. You know you cannot find the absolute value of a potential of a charge unless its infinity is assumed to be, unless the zero of the potential energy, potential is assumed at infinity. Okay, so there also we are creating a reference line. So here also we will be creating a reference line, which will be the change in internal energy. Because we cannot find its absolute value. We cannot say that the internal energy of a certain object is this much, that much. No, we will be looking at change. And in our domain, there are only two ways which we can change the internal energy of an object, which are first of the ways is altering the temperature. As I told you, it depends on temperature, and a phase change. Basically, gases have the highest internal energy, which is also why at the same temperature, 100 degrees Celsius, steam will do more damage to your skin than boiling water. Okay. And gas, liquid, solid, that's expected. And now let's look at what is work done. Work done, as I said, is a path function, and in our context, work done is nothing, but it is transfer of energy not due to the temperature difference. And for any ideal gas, the work done is simply given as area under the curve of external pressure versus volume graph. Keep in mind, this is the external pressure. Okay. And only in reversible processes, the external pressure is equal to the thermodynamic pressure of the gas itself. So the curve of external pressure versus volume, the area under that curve is given as the work done. And this is the magnitude of work done formula. And as per IUPAC, how do we open this mod here? If the gas is expanding, keep in mind this is only in chemistry because physics has the opposite convention. So in chemistry, if the gas is expanding and if the volume graph, it goes like this, the volume is increasing, then the work done is less than zero. And we call this the work done by the system. If the gas is expanding, the work is being done by the system against the surrounding. And if the gas compresses, the work done is taken as positive and the work is being done on the system by the surrounding. And as I told you, physics has opposite convention. So now let's talk about heat and first law of thermodynamics. So heat is, what is heat? It is heat. There is no other way to define it. And it is the energy flown via the temperature diff. See how work was the energy flown without the temperature difference, and heat is the energy with the temperature difference. And physics and chemistry have the same convention in case of heat. Heat given to system is greater than zero and heat released by the system is less than zero. The first law of thermodynamics states that basically the change in internal energy of any process is equal to the work done in the process plus the heat in that process according to the convention that I told you, this convention and this convention. So the first law of thermodynamics is also based on law of conservation of energy, as you can tell. And energy can't be created or destroyed, you know that. But keep in mind, energy is not conserved in a system. It might be, like if it's mentioned in the question, but all in all, the energy is conserved in the universe. Okay. So heat is a path function, as I told you. You cannot contain heat. Well, this line might seem contradictory. Then how are we defining enthalpy as total heat content? It is the potential. Basically, it is the potential that the substance has to generate heat. But all in all, you cannot contain heat because heat is defined as exchange of energy in a process. So now let's look at enthalpy. What is enthalpy? Enthalpy is defined as nothing but internal energy plus the product of pressure and volume at a condition, and the total heat content in a specific state is defined as the enthalpy. Now, as we know, since the internal energy isn't fixed and we cannot pinpoint a direct value for it, the enthalpy isn't a fixed value either. So here also, we will be looking at the change in enthalpy. Okay. And how do we define that? Well, since enthalpy itself is defined as this, it is no surprise that change in enthalpy is defined in this way. And if you want to define the enthalpy change for a reaction, you will have to find the respective delta. What does respective delta mean? Basically, delta is difference. We are expressing difference between two conditions of the system. And in the case of a chemical reaction, those two conditions are going to be the product side and the reactant side. So we will basically find the enthalpy of the products minus enthalpy of the reactants, and this will be our delta H. And using these same limits, we will put those in delta U and delta pressure into volume. So we will be able to look at delta H. And our upper limit is the products and our lower limit is the state of the reactants. But you might be wondering that it is tedious to define delta PV in case of a chemical reaction, because no question ever tells you that pressure on the reactant side was itna, volume on product side was that much. So what do we do? Basically, remember your ideal state equation, PV is equal to nRT. And if we are talking about constant temperature, then delta PV is nothing but T into R into delta N. And you can see that here also. But one small nuance here is that delta N is only for gas moles. We saw this point in equilibrium. Let's look at an example too. If we have solid carbon, graphite plus gaseous oxygen converts to carbon dioxide, which is gaseous, we can see that delta N is equal to 0. How come? Because right side also only has one gas mole and left side only has one gas mole. You will not be counting the solid mole. So since delta N is equal to 0 here, we can see that delta H is equal to delta U. And basically, if we see another term, heat of reaction, what is the heat of reaction? The heat of reaction is basically how much heat a reaction gives or takes on completion, whether it is exothermic or endothermic. At constant pressure, the heat of reaction is equal to the enthalpy difference between products and reactants. And at constant volume, the heat of reaction is equal to difference in internal energy of the products and the reactants. So if the question says what is the difference between heat of reaction at constant pressure and constant volume, you can say it is delta H minus delta U, which according to this relation is also equal to delta PV, which is also equal to temperature into universal gas constant into delta N gases. So now let's understand what a degree of freedom is. Degree of freedom is nothing but it is the number of ways a system can store energy. And basically it can, according to the law of equipartition of energy, every degree of freedom of a system has the same amount of energy. So they are all equal and the system can move, rotate, vibrate in order to store energy. Basically FT. FT is the degree of freedom associated with translation. Basically movement in where the center of mass of the system moves like this. That is translation. And FR is the rotational degrees of freedom. Basically in which this center of mass remains fixed but the body rotates. That is the rotational degrees of freedom. And if we want to calculate, like the calculations which will show up later, I will show you. For those, we will use F, which is Ft plus Fr. And in some cases, the system can vibrate as well, which can make extra degrees of freedom at higher temperatures. And the question will ask you to take extra degrees of freedom accounting for vibration, in which you have to add Ft plus Fr plus Fv, where Fv is the degrees of freedom due to vibration. Okay. So these are some cases you have to know. If the gas is monoatomic, then Ft is 3 and there's no rotational degrees of freedom. If the gas is diatomic or triatomic linear, then Ft is 3 again. Basically, Ft is 3 in every case, but Fr is the one that changes. And in both diatomic and triatomic linear, Fr is 2, since the rotation direction along the axis of the linear molecule is negligible, so it cannot store energy in that manner. So we will be ignoring Fr here. And if it is poly non-linear, basically it has more than 2 atoms as well, and they are not aligned in a linear manner. So Ft is 3 and Fr is also 3. The rotation in that direction is no longer negligible. And this is not final. Maybe the question can ask to add vibrational degrees of freedom as well. So you have to be a little vigilant there and read the question properly. So now let's look at heat capacity. Heat capacity is nothing but it is a constant which relates the heat given or taken by a system to the temperature diff which arises in the system. Okay. So there are two classifications we can make. First of all, on the basis of quantization, the heat capacity, or in other words, the total heat capacity, which is capital C here. How does it relate to the temperature difference? It is a direct proportionality constant between heat and the temperature difference, and it is defined for the whole sample or specimen which we are observing in our system. But small s, or the specific heat capacity, Q is equal to ms delta T. Now this is defined per gram. And similarly, molar heat capacity is defined per mole. Obviously, total heat capacity is equal to mass into the specific heat capacity, which is equal to number of moles into the molar heat capacity. And these all terms, you have to be very vigilant that you don't mix them up, otherwise the question will go wrong. And on basis of condition is the second classification. The heat capacity can be Cp for constant pressure or Cv at constant volume. Both specific and molar heat can be expressed in P and V form. For example, if I want to express molar heat capacity at constant pressure. Then you put a bracket and write M comma P. M signifies the molar part and P signifies the constant pressure part. Okay. And so on. And lastly, the Mayer's relation, which is nothing but it is a universal relation which states that the molar heat capacity at constant pressure minus the molar heat capacity at constant volume is always equal to the universal gas constant. And if we want to write it in terms of total heat capacity, we can write it like this. So I hope you understand it this far. Let's look at the last topic for today, which is the Poisson ratio. And for any gas, the Poisson ratio is nothing, also denoted as gamma. It is nothing but the ratio of Cp to Cv or Sp to Sv or Cmp to Cmv. Basically, all of them will have the same value of gamma when you take the ratio because mass and mass will cancel out, mole and mole will cancel out, so it doesn't matter really. And this is a very useful term which will show up everywhere in this chapter. And these are some important formulae related to degrees of freedom and gamma, which you have to know. As I told, gamma is Cp2 upon Cv. So this is that. And basically the total heat capacity at constant volume can be shown as F by 2 Nr. And I accidentally put the wrong image here, but this was supposed to be, wait a second, let me fix it. So yeah, I fixed it. Give me a second. Yeah, so as I said, Cv is equal to F by 2 Nr. This is the total heat capacity here. And if you want to show the molar heat capacity, just take N to this side and it will become Rf by 2. And if we want to look at the total heat capacity at constant pressure, it is F plus 2 by 2 into Nr. And this is very important that the change in enthalpy is NCP delta T, but the change in internal energy is NCV delta T. So using these two equations and these two equations and this equation, we can say that delta H is equal to gamma times delta U. And lastly, gamma and degrees of freedom have a direct relation, which is gamma is equal to 1 plus 2 by F. So this is all for today. And in the next lecture, we will be looking at the types of processes: reversible, irreversible, isobaric, isochoric, isothermal, adiabatic, everything we will see in the next part. And basically they were meant to be in this part only, but I could not make it on time since I had to do some important work. But well, I will not be giving the notes right now, but after the chapter ends. So just take screenshot if you can. I'm showing you all the slides. And that's all for today. Thank you for attending and please share so I can be happy.